All right, well, welcome to the second tutorial for this section. In this tutorial, I'll walk you through some of the probability rules that you should already have read about and some example calculations that you should be able to do. All right, so the first rule that I'll walk you through is the addition rule. And this first one, we're going to go through an example looking at the rolling of a single die. And admittedly, the steps here are a bit simple, and you can probably figure this out without doing the math behind it, but it's incredibly useful to walk through an example where we could figure out the answer very simply so that we can better understand the steps involved. This way, when you get to a more complicated problem on an assignment in lab, on an exam, you'll better understand the steps that you need to take mathematically in order to calculate the probabilities and answer your question. All right, so whenever we're doing any probability question, we have to consider the entirety of our probability space. So what this means is that we have to think about all of the possible outcomes, and then the probability of all of the possible outcomes has to add up to 0. So if we are thinking about a single dice, or a single die, it's a 6-sided object, and down on the bottom right-hand corner, I've shown you the only 6 possible outcomes that you could achieve, okay? So if we were to write this more formally, like I've done up here, we have the probability of getting a 1 plus the probability of getting a 2, a 3, a 4, a 5, and a 6. We add up all these probabilities, and they have to sum up to 1. Okay? Now, if what we were interested in is the probability of getting a 1, a 2, or a 3, we would write it like this: P, 1 or 2 or 3. And in this case, these are 3 independent outcomes from rolling a single die. They are 3 completely unique ways to get one of these answers of interest, one of these outcomes of interest. So we could get a 1, or we could get a 2, or we could get a 3. And I know that at this point this seems incredibly simplistic, but it's very important to recognize that these are independent outcomes. They are not overlapping outcomes. Okay? We can only get whole numbers on these dice. It is impossible to get more than one number at a single roll. We can't have a 1 and a 2 on one single die in one roll. Okay? This is very important because what this indicates to us is that this is the simple addition rule that is called for. If we could get more than one outcome at the same time, then it would be the generalized rule, not the simple rule, that we would look to. Okay, so in this case, with this simple question, and we're looking at the dice, and we're going to roll the dice. If we are going to roll once, a single die, and we want to know the probability of getting a 1 or a 2 or a 3, we would simply add the probability of getting a 1 or a 2 or a 3. And because there are 6 sides, we know that the chances of this happening are 1 in 6 for each of these options. So the probability of getting a 1 is 1 in 6, the probability of getting a 2 is 1 out of 6, the probability of getting a 3 is 1 out of 6. So we add this up, we get 3/6 or 1/2. And because this is a simple problem, because I've shown you the 6 outcomes down on the bottom right-hand corner, you can look and verify for yourself that yes, this math is correct, following the simple addition rule. All right, now let's consider a slightly different case. Here, we want to know the chance of getting a number 1 through 3 or an even number. So we would write it like this. There are many ways that you could write this, but when you are doing your problems, you want to make sure that it is clear what you mean in these parentheses. So here I've said P, 1 through 3, or even. So to look at how this could happen, we could roll a 1 or a 2 or a 3, or we could have an even number. So the even numbers are 4 and 6, or a 2. But what you should notice here is that this leaves us with one value that shows up twice, the 2. So the simple addition rule that we just saw would count this 2 more than once, and it would give us an inflated estimate. So in this case, we're going to want to use the general addition rule. So we add the probabilities of each outcome of interest. So the probability of getting a 1, a 2, or a 3, plus the probability of getting an even number, but then we subtract out the chance of getting a result that simultaneously meets both criteria so that we don't double count anything. So this is why we subtract out the probability of getting a number that is a 1 through 3 and even. And because the 2 satisfies both of these criteria. So 1/2 plus 1/2, and then we have to subtract out 1/6, and that gives us a probability of 5/6. So remember that we calculated this probability of getting a 1 or a 2 or a 3 on that previous slide, so that's where that 1/2 came from. And then half of the outcomes here are even numbers, so that's where this 1/2 comes from. And of the 6 outcomes, only one is both even and between the numbers of 1 to 3. So that's where those 3 fractions in our calculation came from. Okay, now I'd like to go through a few examples looking at the multiplication rule. And for this example, let's take a look at rolling 2 dice at the same time. And as an example, I would like to look at the odds of rolling 2 6s if we roll 2 different dice. Now, there's only one way to have this outcome, rolling a 6 on the first die and then rolling a 6 on the second die. So we multiply out the odds of getting the first 6 and the odds of getting the second 6. So this P6, 6, that is just another way of writing P6 and 6. Okay. And to get this, again, we're going to multiply the probability of getting a 6 times the probability of getting a 6 on the second dice, or the second die. And these are independent of each other. This means that what you roll on the first die doesn't affect or dictate in any way what you roll on the second. So a 1 out of 6 chance of getting a 6 on the first die times a 1 in 6 chance of getting a 6 on the second die. This gives you a 1 in 36 chance of rolling 2 6s if you were to roll 2 dice. And because getting a 6 on each of the dice were independent outcomes, it's not possible to get 2 6s at the same time. We can't roll a single die and have 2 6s show up on one side. Okay? So this is an example of the simple multiplication rule. All right, now let's take a different case, and here we want to find the odds of rolling a 5 and a 6. So in this case, there's 2 different ways that this can happen. Okay, on this table down here, we have roll 1 shown in red, roll 2 shown in blue, and if we want to look at the cases where we get a 5 and a 6, we could roll a 5 and then a 6, or we could roll a 6 and a 5. So we'll add together the probabilities of each of these things happening. Okay? Meaning that this involves the usage of the addition rule here, but the calculation of each of these components, the probability of a 5 then a 6, and the probability of a 6 then a 5, both of these are going to utilize the multiplication rule. Okay? And this breaks down into the probability of getting a 5 multiplied by the probability of getting a 6, plus the probability of getting a 6 times the probability of getting a 5 on that second die. Right. So this showed us here how to use the multiplication rule, but with some of the addition rule in there as well, so a combination of the 2 rules. And we see the components here, 1/6 times 1/6 plus 1/6 times 1/6, and that gives us 2/36 or 1/18. Okay, so this is an example of when we have to utilize both multiplication and addition. And it's actually very common that we'll have to use both multiplication and addition to answer a single probability question. Okay, so now I'd like to take a different approach. And in this next example, I'd like to see what the probability of rolling 2 dice and not getting any 6s would be. So this is a bit different way to ask this question. So for this example, we're looking at this space of possible outcomes. Now, we could just add up the number of squares that we see here, but we need to know how to do these steps mathematically. Okay? So the probability of no 6 in 2 rolls, we can write like this, P no 6 in 2 rolls. And that's going to be equal to the probability of no 6 in 1 roll times the probability of no 6 on the second roll. And the probability of no 6s in one roll is equal to 1 minus the probability of getting a 6. Okay, so this probability is equal to 1 minus 1/6, or 5/6. So taking that back to our original equation for the probability of no 6s in two rolls, that's 5/6 times 5/6, or 25/36. Okay, so there's a 25/36 chance of getting no 6s at all in two rolls. Okay. Now the next thing that I'll show you is an extension of the multiplication rule. And we call this extension the at least one rule. And this is going to tell us the probability of getting at least one outcome of a particular type out of a number of chances. So we're looking at a number of chances here. So that means that some of the outcomes could match the outcome of interest, or a handful of them, or all of them could meet or could match that outcome that we're interested in. But the only thing that matters is that at least one. Okay, so that's why we call this the at least one rule. All right, so we're going to look at the probability, using dice again here. We're going to look at the probability of rolling at least 1/6 in 4 rolls, okay, which we can shorthand as just P, 1, and 4. Okay. All right, so we can write it like this: P, 1, and 4. It's going to be equal to 1 minus the probability of not rolling a 6 in 4 rolls. Okay, so we want the probability of rolling at least 1/6 in 4 rolls. So in order to get that, it's going to be 1 minus the probability of not getting a 6 in 4 rolls. Okay? And to get this, it's 1 minus P not a 6 raised to the 4th. And the reason that we've raised it to the 4th power is because we're looking at 4 rolls here. All right, so if we take that back to our original question, okay, we have to look here at the probability of not getting a 6. Okay, the probability of not getting a 6, as we saw before, this is 1 minus the probability of getting a 6, or 5/6. Okay, so P, 1, and 4 is equal to 1 minus 5/6 raised to the 4th power. So if we do the math here, which you can do in Excel, you can do on a calculator, it's probably going to be most useful for you guys to be doing this in Excel, because that's where you're going to be doing most of the other calculations that you're doing for class. So 1 minus 0.482, or 0.518. Okay, so there's a 0.518 chance of getting at least 1/6 over 4 rolls. So about a 52% chance. All right, so the previous cases that we just finished looking at, they were all examples in which the probability of getting one outcome was independent pretty much of the probability of getting any other outcome, okay? Because we were looking at dice, and dice just have a single outcome on each side, okay? So we didn't have any conditional probabilities, okay? Now I'd like to walk you through some examples where we do look at conditional probability, where the odds of 2 or more outcomes are not independent. Okay? So the probability of A and the probability of B are not independent of each other. All right, and in this example, what we're going to do, we're going to look at some data from medical residents. Okay, so here, again, I've put on the top of the slide here, probability of A and the probability of B are not independent. And in this example, we are looking at some data from some recent survey data from medical residents looking at specialties. And I've selected just of interest 2 topics here, so female and pediatrician as our categories of interest. And the data show that 45% of residents are female, so 0.45. And the data also show that 7.6% of residents are pediatricians. So if we were interested in the proportion of residents that were female pediatricians, okay, so female and pediatrician, we can try multiplying the probabilities of being female and of being a pediatrician. Okay? That gives us 0.034. But it turns out that that's totally wrong. Not the right way to do this question. This is not how you would get the overall fraction of residents that are female pediatricians. And the reason that this doesn't give us the right answer is because the probabilities of these two things are not independent of one another. Okay? So the probability of being a female resident and being a pediatrician are not dependent of each other. So what we need to know is the conditional probability, which we have in the form of the likelihood of being a female given that you are a pediatrics resident. Okay? So notice this notation that I'm using here to indicate the probability of being a female given that you're a pediatric resident. So the probability of A given B. And from these data, we know that this number happens to be 0.73. Now, 0.73, this is quite a bit different than that proportion of female residents overall. Proportion of female residents overall being 0.45. And you'll notice that the way we represent this conditional probability, like this, okay, remember this notation because this is the notation that we'll use throughout the course when we're doing our probability questions. All right, so the probability of being female and a pediatrician is equal to the overall probability of being a pediatrician multiplied by that conditional probability of being a female given that you are studying pediatrics. So this is 0.076 times 0.73, which gives us a value of 0.055, which is quite different than that value of 0.034 that we originally calculated incorrectly when we didn't account for the fact that these two things are not independent. Okay? So always be looking for whether or not you have conditional probabilities in your question. Okay, so I'd like to go over a brief example of how you can do some of these probability calculations in Excel. And I actually like to use Excel for a lot of calculations, not just ones that are more complicated, because you can easily enter your equations just like you would on a calculator, but you can quickly update things and you can go through and troubleshoot and also figure out where things aren't working if your equations are a little bit off. Alright, so for this example, we'll just look at a couple different example questions here. So for example, if we look at the proportion of males, and here we can put probability. So if the probability of being male is 0.5, one thing that can also be useful when you're working through probability questions, like you'll see for homework, is to also include the probability of not meeting that case. So in this case, this is just going to be 1 minus the probability. So here just equals 1 minus this. Alright, so the probabilities have to add up to 1. So if the probability of being male is 0.5, the probability of not being male is 0.5. Now let's take a look at the probability of being blonde. So let's say that the probability of being blonde is 0.2. Okay, we can now drag this down. If the probability of being blonde is 0.2, then the probability of not being blonde is 0.8. That's what the probability and probability of not mean here. Alright, so now let's get a little bit more complicated here. And let's look at the probability of being male and being blonde. Okay, well, this, as you may remember, should be just a case of the multiplication rule. So here, the probability of male and blonde is simply equal to the probability of being male multiplied by the probability of being blonde. So here we can see the probability of 0.1. So this is a case of the multiplication rule. And if we just want to copy this down, okay, so what this means here, the probability of being male and blonde is 0.1, and the probability of not being male and blonde is 0.9. Alright. What about the probability of being male and not blonde. Well, this is where it comes in handy to have this column of data calculated for you, because here the probability of being male and not blonde would be equal to the probability of being male multiplied by the probability of being not blonde. So 0.4. And we can copy, move this down. This is another case of the multiplication rule. And now what if we want to look at the probability of at least one blonde male in 5 kids? Okay, so if we want to look at the probability of at least one blonde male, that is, in 5 kids, here we're looking at a case of that at least one rule. Okay, so one of the 5 kids could be male and blonde, or it could be 2 or 3 or 4 or 5, just as long as one of them is. So remember that at least one rule is equal to 1 minus the probability of not meeting these criteria, so the probability of not being blonde and male. So being male and blonde is 0.1. The probability of being not male and blonde is this 0.9 here. So 0.9. And remember, the other important part here is that we're going to raise this to the 5th power. And we're raising it to the 5th power because I said 5 kids here. Okay? So 0.40951, so about a 40% chance of at least one child out of 5 being blonde and male given these probabilities. So this is just a quick example of how you can do some of these probability calculations in Excel. You want to make sure that you clearly define what it is you're looking at. It can also be helpful to make just another column out to the side, just indicating to yourself what does this value mean. Okay, so that was just a brief video explaining to you some of the ways that you can use Excel to do some of these calculations for you. Even if they're a bit on the simple side, it is often very nice to have everything written out nicely in front of you, get your formulas in there, that way you can go back and you can double check things and you can have it all nicely in front of you. In addition, it's also going to be very important on exams in this class for you to get in the habit of notating your work so that somebody else, i.e. me, can look through it and grade it for you. All right, now the next topic that I'll go through with you is Bayes' theorem. And Bayes' theorem can get a little bit complicated, so I wanted to walk you through it in tutorial form. Here you can see 2 versions of the equation. The top is the simplified version, and on bottom we have the expanded version of the equation. And as our example to walk through Bayes' theorem, we will examine the probability that a woman that has been diagnosed with breast cancer actually has breast cancer. So essentially what we're kind of getting at with Bayes' theorem in this example is the false positive rate versus the accurate positive rate of a test. So in this case, a woman has been diagnosed with breast cancer, and after getting that initial diagnosis, what are the odds that she actually has breast cancer? Now, the idea of Bayes' theorem is that you can reverse the conditional probabilities. So if you know the conditional probability of B given A, and you know the overall probability of B and the overall probability of A, and these are color-coded here, then you can calculate the overall conditional probability of A given B. Okay, so now what I'm going to do is walk you through a short video in Excel showing you how you can calculate out the components of Bayes' theorem, and also, just as important as getting the right numbers, how you would interpret those numbers. Okay, so as we move over to Excel here, we will take a look at how we calculate the components for Bayes' theorem. So in this case, what we will do is look for the probability that a woman actually has cancer if she's been diagnosed with cancer. So in this case, we're looking at some data for breast cancer. And we'll base this on the chances of being diagnosed when you actually have the cancer. Now, in the shorter form of the equation, which you see up here, in the shorter form of the equation, we would have to know the chance of actually having cancer and the overall chance of being diagnosed. But more typically, we don't know the overall rate of positive diagnosis. So what we can do is use this expanded version of the equation, which I've shown you down here and which you also have on the handout for probability. And in this expanded version of Bayes' theorem, which I know looks a little bit scary because there are a lot of components to it, it actually has the same numerator. If you notice this probability BA, probability A, this is the same here. And there are a lot of components in the denominator here, but it's actually calculating the same thing. But the components that are being used are things that we're more likely to have access to. So on the top is the probability of having a positive diagnosis if you have cancer, times the probability of having cancer. And on the bottom, we have the overall probability of being diagnosed positively, which we get by multiplying the chance of getting diagnosed if you have cancer, but we also include this other component, the component of not being diagnosed if you don't have cancer. So, how do we calculate this? Well, if we set this up here, I already have some headings in place, so we're going to look at the component, the probability, and we'll just make a nice little handy cheat sheet of what the component actually means. Okay, so if we look at a few different things here, so we will look at the probability of having cancer, PC, and this we know from the data is 0.01. Okay, so this component right here is the probability of having this type of cancer. And then the probability, or pH, that right there is going to be the probability of being healthy. So the probability of being healthy is simply equal to 1 minus the probability of having cancer. So this is really the probability of cancer versus probability of not cancer, shown here. So then we'll also go ahead, we can calculate the probability of receiving a positive diagnosis if you have cancer. We know, so this isn't actually a calculation, we know from the data that this is 0.8. Okay, so this is the probability of a positive diagnosis if you have cancer. And then the next bit of information that we'll put here is the probability of getting a positive result if you're healthy. So this is the probability of positive diagnosis if healthy. So this would be the false positive rate. And we know from the data, this isn't anything that I'm calculating, this is a component of Bayes' theorem, or that we can use a Bayes' theorem here, that we know from the data. Okay, so our source here, this comes from the data, this comes from data, and this up here comes from data. This is simply 1 minus the probability of cancer. And if you try to enter parentheses C parentheses, you might have copyright pop up, so that's why I entered those extra spaces there. Okay, so now we can go ahead and calculate some components of Bayes' theorem, and it's actually a bit useful to go ahead and calculate some of these components separately and then combine them just so that you can see a little easier where these values are coming from. So here we're going to multiply the probability of getting a positive result if you have cancer by the probability of having cancer. So this is simply equal to, we've already calculated this component, this times this. Okay. And then other component that we need here is the probability of receiving a positive diagnosis when you are actually healthy times the probability of being healthy. So again, this is equal to this component multiplied by this component. Okay. Now we can go ahead and do our calculation for Bayes' theorem. So what we need to calculate is the probability of having cancer if you get a positive result. Okay, so this is flipping this Bayes' theorem around. All right, so calculating out Bayes' theorem here, we see that is equal to this component here, the probability of receiving a positive diagnosis if you have cancer times the probability of having cancer divided by this component here, okay? Probability of receiving a positive result if you have cancer times the probability of having cancer plus the probability of not being diagnosed when you do not have cancer. Okay? So this gives us a value of about 0.08. So another thing that can be a little helpful here, if we sort of look at the components that we have defined here, and let's put them in terms of the equation over here. So when we look at these values, the probability of having cancer, this would be equivalent to the probability of A over here. Here the probability of being healthy would be the probability of not A. The probability of receiving a positive diagnosis if you have cancer, this would be the probability of B given A. And here the probability of receiving a positive result if you're healthy, this would be the probability of B given not A. Okay, so this is how we calculate this. Now, one thing that is quite interesting is that this actually surprises quite a few physicians, which is a little bit disconcerting, especially if they are physicians that study cancer and they are in the business of giving diagnosis and have to deal with false positive rates and things like this. What this is telling us, this probability, C given positive, this is telling us the probability that a woman that is, given that she has been diagnosed with cancer, it's telling us the probability that she will actually have cancer. So we can see that at 0.07 here, this is about an 8% chance. So what this means is that the actual chance of having breast cancer when you have received an initial diagnosis from a mammogram is actually quite low, only about 8%. And the reason why this is so low is that even though the chances of a false positive, okay, remember the false positive rate was here, not quite 10%, even though this false positive rate is fairly low, so many more women don't have cancer than the women that do, that even this small fraction of not quite 10% adds up to a really large number of women altogether. So the few women that have cancer, and so few women have cancer that the number of positives that are generated from those women that receive positive diagnoses that actually have cancer, it's still a relatively small number. So the fraction of women that end up getting false positive results from a mammogram ends up being quite high, and the fraction of real true positive results from a mammogram ends up being quite low. Okay? And just to go ahead and put in here what it is that I just said in my explanation of Bayes' theorem and what it's telling us here, this is how we would interpret these data for Bayes' theorem. All right, so the very last thing that I want to go over in this tutorial is combinations and permutations. So here, pasted in from the handout that I provided you with the equations for all of the different statistical things that we're doing this week, is the equation for combinations and permutations. And what combinations and permutations are, this is sort of the ways that you can get particular outcomes. So, for example, if we think of an example where we are looking at kindergarten snacks. So here we have 5 options. We've got cheese, crackers, apple, banana, and carrots. Okay, so there are 5 choices. Okay, and you're allowed to, or the kids are told that they can choose 3. So in this case, the number of options, n, would be 5, and the allowable number, 3, is x. And you can see in these equations here, for both combinations and permutations, both of them have n factorial as the numerator. And if you either remember from elementary school, high school math, or you've done the reading like you should be doing, and you remember that factorial is multiplying a number and all of the subsequent numbers together. So in this case, if n is 3, n factorial would be 3 times 2 times 1. Okay, n actually here is 5 and x is 3. But the numerator is the same. But where we have a difference is in the denominator. And the reason why we have a difference is because combinations look at how many different ways you can put together these options when order doesn't matter. Permutations, these are a little bit different because with permutations, this is when order is important. Okay? So when you are given a question, ask yourself whether or not order is important or not, and that will dictate whether or not you need to be looking at the formula for combinations or permutations. Okay. Now we're going to look at a short Excel video that I've recorded for you, showing you how you would calculate these 2 things separately in Excel. Okay, so as we just looked at, combinations and permutations are a way to look at the number of arrangements that you can have of your variables. And the first thing that I'd like to take a look at is this example with the kindergarten snacks. So here we've got 5 snack options. Let's show over here. We've got cheese, crackers, apple, banana, and carrots. And if the students are instructed to pick any 3, it doesn't really matter what order they choose them in because they're all going to go on their plates and then they can eat them or throw them on the floor or whatever happens with kindergarten snacks. Okay, so because the order doesn't matter here, this would be an example of a combination. So here I'm going to walk you through how you would go about calculating the number of combinations that you have. So when we look in this equation that you see down here, we need to define what the n and the x are. So here we put n and we put x, and then it's also handy to just go ahead and calculate out what n minus x is as well. Okay, and then I'm also going to, since we need the factorial here, I'm going to calculate out the factorial, and it's always handy when you, especially when you are going through and learning this to begin with, to have just a little cheat sheet column here that lets you know what it is you're looking at. Okay, so n here is going to be the number of possible choices. X is the number that can be picked. Alright, so we know here we have 5 snack choices, so n would be 5. X, we're told that the students are allowed to pick 3, so x is 3. And then we can enter a nice easy formula here. And obviously you don't really have to enter a formula, we could just enter 2. But if you ever want to change your numbers here, you will not have the formula set to do that. Okay, now you remember from the reading that factorial is, so 5 factorial would be 5 times 4 times 3 times 2 times 1. But Excel has a handy feature, fact, okay, and then we just enter the cell. Now you could enter a 5 here, but if we click in the cell, then of course this is a formula and it's going to update. for us. Okay, so then we want the factorial for x and also for n minus x, so we can just drag that down. And so then our combinations, if we want to see how many different combinations we have here, okay, looking at the equation down here, the number of combinations is going to equal n factorial divided by x factorial times n minus x factorial. Okay? And you see 40, I actually entered that formula wrong. Okay? And I did that on purpose to remind you about the importance of parentheses here. So if we take a look real quickly at what is happening in this formula, and again, look up in the formula bar here. So my formula is E6 divided by E7 times E8. So what's happening here is E6, 120, is being divided by x, which is 6, or x factorial rather, which is 6, and then that whole fraction is being multiplied by n minus x factorial. So we need to make sure that we put those parentheses in the right places because it's very easy to make a mistake. Okay, so use parentheses liberally so that you can avoid making those mistakes. Alright, so the number of combinations is 10. So we can also do this another way, because if you remember from that formula sheet that I gave you, Excel has a nice easy combinations formula. So it's equal to combin, so we can just hit tab when we see the formula that we want pop up. And remember, they always give you these helpful pop-up tips. Okay, so the format that this formula has to be in is combin, then in parentheses, the number, comma, and the number chosen. Okay, so that's going to be n, comma, and the number that can be chosen. So 10. So you can see that doing this either way is going to get you the same answer. But because we have this equation that we can use in Excel, it's often going to be easier for you to just go ahead and use the combin equation rather than typing the numbers in. But do what works for you, either going to get you the right answer. Okay, so this was an example of combinations, okay, because the order didn't matter. Now, in contrast, let's take a look at maybe you are helping name somebody's child, okay? And maybe you have been watching too many comic book movies, and you have this list of Norse names that you're interested in. Well, you're told to pick any 3, okay? So again, we're picking 3, and you can see I have the information in here that I'm going to go through and show you, but I'll sort of walk you through it. Alright, so if you have to pick any 3 of these names over here, again, we have 5 choices: Thor, Odin, Loki, Magnus, and Bjorn. Alright, so we've got 5 choices, and you're told to pick 3 names. Well, in this case, the order is going to matter, because the order of the 3 names is going to give you a completely different name. Alright, so here we have the same, notice that we have the same components here to our equation. Alright, so here again we have n is equal to 5, x is equal to 3, okay, and then again just n minus x, and then if we want our factorials, now you could just copy this from above because you know it's the same, okay, and again this n is going to be the number of choices, and this is the number that can be picked. Now, to do permutations, okay, we can also do this in 2 different ways. So, and I'm showing you this just so that we can satisfy that curiosity and know that yes, indeed, it is going to calculate the same thing. So, remember we have our factorials in this column, so permutations, the equation is here. That's going to be equal to n factorial divided by, and let's go ahead and get our parentheses right to begin with, here we don't have to actually do n minus x factorial because we've already calculated that. N minus x is 2, and n minus x factorial is here. Okay, so we didn't need those parentheses, but it doesn't really matter if we enter them or not. Okay, so we see that there are 60 different permutations when order does matter. Okay, but we also have the permute function. So we can use the permute function. Again, the components that it needs are number and the number chosen. Okay, so here you're going to be clicking in these cells where you have your number and your number that can be chosen, rather than using the factorial cells that we calculated here. And you can see that, no big surprise, it doesn't matter if we calculate it by entering the equation components ourselves or by using the permute function, we're going to get the same answer each time. So, given the same scenario, okay, 5 choices, and being able to pick 3, when we look at the difference here between the number of permutations and the number of combinations, we see that there's a pretty big difference here. And there is a big difference because here, in a combination, the order doesn't matter. So cheese, crackers, apple is going to be the same as apple, cheese, crackers. But down here, it does matter because a name of Thor, Odin, Loki is going to be a different name than Odin, Loki, Thor. Alright, so this concludes the tutorial looking at combination and permutations. Okay, so as we conclude this tutorial, I'd just like to acknowledge that, yes, I am well aware that this section does go into some challenging material. And while some of the probability problems that we will look at, both as examples and assignments on exams, etc., are going to be fairly simple, some of them will get quite complex. So it is important that you practice going through some of these examples that I'm going to give you, that you understand these basic rules, and that if you don't understand these basic rules, you practice, practice, practice. We do have some basic rules, though, that you can work with as you process through questions. All right, so first of all, ask yourself whether what you are looking at is an and or an or type of question. And also whether there are any conditional probabilities or non-independent outcomes that you need to deal with to get you on the right track to start with. Okay? If it's an or type of question, then you should be thinking about the addition rules. If it's an and type of question, well, then you should be focusing on the multiplication rules. Now, among each of these, there are a simple and generalized versions. And I would say that when in doubt, you should just go ahead and use the generalized version of the equation. Using the generalized version of an equation when the simple version would suffice, yes, you're going to calculate more components. You're going to make it a little bit harder on yourself to answer the question. But if you're not entirely sure which one you should use, that's going to make sure that you don't leave anything out and you arrive at the correct answer. But remember, if you have outcomes that are totally independent and unique, this is like rolling of a single die, and you can get a 1 or you can get a 5. You can get either, but you can't roll the dice once and get a 1 and a 5 on the same side. It's impossible. Okay, so they're completely independent and unique. Okay, this is the case where you would use the simple rule. In this case, a simple addition rule, if we were looking at that question. But if the outcomes can happen together, like being between a 1 and a 3 and also being even, that would be a case of using the generalized addition rule. Likewise, if there are no conditional probabilities in an and probability question to consider, then the simple version of the multiplication rule will work just fine. But if you have conditional probabilities, then you're going to have to account for that using the generalized rule. And of course, as we saw, we can have lots of cases where you have to use both addition and multiplication to find the proper answer. And finally, of course, I just want to make a point that this is a more broadly applicable topic here. So we're talking about probability in the context of a biology class, of course. But just think for a moment about how many times you've heard people in your life talk about odds or chances or likelihood of something happening. Well, all of this is probability. So understanding probability may be a little bit of a challenge at first, but once you practice this and sort of figure out how to answer these types of questions, this is going to be a widely applicable and useful life skill for you to have.